Hello, hello, good afternoon. Hi, good to see you. It's amazing to see some of you on screen. Like, not amazing, it was more amazing to see you in person in Hania, in Crete. But it's great that you are on track with our email, with our second part of the event. So thank you very much for joining. And now the students of this course, if you can turn on your virtual Zoom background screen, please operate a little wait for everyone to connect. And let's see that the chat is working. I would really want to make sure that the presenting students are connected today. We have a few presentations left from our conference last week that started last week. I know that Jonathan is here ready to pick up from where we left abruptly because we were asked to leave the venue. It was too late and we needed to stop. Unfortunately, again, our apologies. So sorry to the students who couldn't present during one dedicated session, but we are committed to giving you the floor and listening to your presentations today. So Jonathan is here. We are also expecting some students from Ukraine who will join us. We have a student from Italy. So please confirm in the chat that you're here and ready to present. Okay, Agustina is there. Hi, hello, Italy. You see, Agustina, you're not exercising, you're not prepared with the virtual background thing.
Yeah,
We're so observed in the real venue. Physical venue of the events. Okay, no worries, no worries. Okay. Okay, other than Jonathan, do we guys have another 2 or 3 presentations that we were expecting today? Let's see. I will also, in the meantime, announce that next week we are hosting a guest lecture from the United States, an expert in AI integration in higher education. Very, very interesting speakers, so something to look forward to. In 2 weeks, I'm going to stop the music perhaps. Our AI-generated music that we created for this conference. Good. Sharing. You can open your camera so we can see you. That would be amazing. Share, stop share. Okay. All right, so Shai, hi, we can see you. We can see Omri, our amazing hosts for AI Icon. Pablo, hello, are you ready to present? You're the one who we're looking forward to as well. So we have Jonathan, we have Pablo. Who else? Who else? We are, I think there was Nikita. I don't see Nikita yet. Maybe he's joining soon. And another student from Italy. You guys should remember, right? Our program. So let's hope it works. So next week we have a guest speaker from the United States. In 2 weeks we have another guest speaker, Professor ERASMUS from Israel, from 2 institutions, University of Haifa and the Technion, an expert in AGI, AI agents. A really interesting talk and session. So guys, get ready. It's going to be very, very interesting. In 2 weeks, I will send you a reminder. Following on our first part, so last week we had a hybrid event, which was quite a challenge, and we enjoyed a lot. We enjoyed meeting each other face to face. We enjoyed, of course, following your presentations, whether you were online or on site in the conference venue. And this week we are continuing with our part 2 with some remaining presentations, amazing presentations that would like to hear from our students. After that, Professor Kostas Petridis will pick up, and finally, we get to have our session about the impact of AI in higher education, presentation skills, plagiarism. We'll see where the discussion takes us. I'm giving it to Kostas to lead the second part of today's session. In addition to our presentations and a session led by Kostas today, I will try to announce some additional tasks that you have on Moodle. So one of the tasks is actually reflection and feedback for this particular event, for this conference. I'll show it to you later. And that's it, guys. I think we can start with our hosts. Omri, Shai, say hello to everyone. Introduce the first speaker.
You want me to start or you start?
Yeah, Shai, you start now.
Okay, so welcome everyone to AI Icon Part 2. I hope everyone enjoyed the first part because to continue from where we left off. Our next presentation is actually our also previous presentation, which is AIMCO, Artificial Intelligence in Military and Cyber Operations. So I think Jonathan should take the stage now. Clap.
Okay, I'm gonna share my screen. Just give me 1 second. Can everyone see my screen?
Yes, perfect.
Okay, so good afternoon, everyone. I'm Jonathan, and my presentation is basically an addition on what Roy, Lior, and Shamia did last week on the integration of AI to military. And the part I'm gonna represent is actually the future use of quantum computing in military with the help of AI. So yeah, it's about quantum computing in short, and of course AI. And first, let's have a brief look at what quantum computing is. So traditional computers, like the ones that we all have right now, it actually use binary bits. It's either 0 or 1. Quantum computers, on the other hand, use qubits, which can exist in a superposition of both 0 and 1 simultaneously. So it's basically like overlapping a lot of dimensions of the bit to create a much more sophisticated system that can actually allow quantum computer to process and store information in a more powerful way, especially in terms of refining algorithms for low complexity for things like probabilistic analysis. And that's actually very important when it comes to predicting the future or things that are actually useful in science and military. And when this technology is combined with AI, it actually opens powerful possibilities and can be used for multiple purposes in military. So the first thing is that it enhances data processing for intelligence. In modern warfare, enemies are usually communicating in encrypted languages, and the efficiency of unraveling the code of encryption is key to a strategic success. Quantum algorithms can process massive datasets rapidly, making them vital for better counterintelligence and signal interception. In this situation, AI can help classify, prioritize, and analyze intercepted data so that quantum computing can effectively accelerate the decryption process. Quantum computing also enables simulation for training and strategy development. It is necessary to train the military for it to be ready for all sorts of uncertainties and adversaries, and thus, modern militaries are conducting drills to simulate real-world challenges. But in the future, all these can be even more computerized with quantum computing and AI. They can primarily allow real-time tactical simulations with all the advances of quantum algorithms accompanied by the analysis of AI. With both technologies emerging and improving themselves to be more versatile and applicable, we can inspect the simulations to get responsive feedback infinitely close to fit to reality. And therefore, quantum-enhanced simulations reduce the need for expensive physical exercises and improve preparedness of the military. With these advanced applications, we can also use them for real-time decision-making in extreme scenarios. For instance, in military operations involving combat, where things can change drastically within a matter of a split second. Quantum-enhanced AI can process vast streams of data to help commanders respond in real time. This can be made possible with the help of two methods. The first being sensor fusion, which involves integration of diverse data sources like radar, satellite, and infrared from a cohesive battlefield view, something that can also be utilized with quantum computing to make the fusion more synchronized by reducing the inevitable latency of compilation, which is significantly less compared to pre-existing computing methods. Beyond the sensor fusion that is more feasible with quantum computing, AI plays the role of predictive modeling by anticipating enemy movements and suggesting tactical responses. With these two combined, combat can be much more intelligent in scenarios that are impossible for computers to process and send corresponding signals in time. Last but not least, with the boost these technologies give to military in terms of counterintelligence, realistic simulation, and real-time combat decisions, we can apply them to complex defense systems. This is especially the case with advantages of quantum computing and AI for more accurate models of battlefield dynamics. Such precision and accuracy are even more demanded in missile defense and countermeasure systems. With the help of the more responsive quantum computing and AI trajectory prediction, we can produce a more exact system for tracking the path of missiles within the limited time span that is still operationally practical to strike them down. This not only helps us to defend ourselves, but also gives us access to real-time decisions on the need for defense while making it effective. In this way, air defense systems can both respond perfectly to threats from the sky and save money from redundant weaponry against the missiles that will land on open areas without actual economic or humanitarian loss. In summary, quantum computing, particularly when integrated with AI, will potentially transform military operations by enabling faster analysis, smart encryption, enhanced simulations, and more responsive defense. This technology will be a cornerstone of the next generation military system. And that's all. Thanks so much for listening.
Thank you very much, Jonathan. Questions? Okay, we do have some questions. I think the topic is really hot. Maybe Shai and Omri, you can also lead the discussion.
Felix, sorry. I see two questions, right? Two hands raised. Let's do Costas first.
Thank you. Thank you very much, Jonathan, for the topic. It's indeed a very interesting topic with a great potential. However, there are large challenges. I would like to ask you two questions. So the first one, indeed, using qubits than bits, you have fundamentally an infinite amount of options. You don't have just 0 and 1s. You have anything related to the spin of the electron and the direction of the electron. That's why, we have the quantum computing. However, there is a challenge about the temperature that we need to operate the quantum computers, which means, it's below 0. I mean, it's below the room temperature, much below the room temperature. So how can we address this kind of issues if we are going to operate this kind of devices in the field? Any ideas? I mean, I know that the research is moving towards room temperatures, but your ideas?
Okay, so I think I can address the problem of quantum computing. So that's not exactly included in my speech, but honestly, and the fact is that quantum computing has a lot to go. And even when quantum computing is going to be very well designed and very ready for its advantages, it's not going to make the traditional binary system obsolete, because there are still many fundamental advantages that binary bits are having than qubits. So the first thing the main thing they're asking me is about how we're gonna operate these under the temperature, below 0. And that's right, it's very hard to maintain that quantum computer, because you have to make as possible less entropy as possible. You cannot make a very thermodynamically unstable system. It has to be in a very ideal situation, with a temperature as low as possible. That's what that concerns a lot of people in the field. And I think that's not the only problem. Like there are a lot of problems coming with quantum computer. It's not just the temperature. Like there are so many problems. There are things that's called decoherence, or things that kind of means that the quantum state can't be maintained. So the storage, the storage of the computer is very hard to be stored the way that we store things in our hard drives with binary system. There are a lot of problems yet to be solved, and not to mention let alone like AI, and like still the AI integration to quantum computer is still conceptual. It is like not really something that is very established, but it's a foreseeable future. Because like when it comes to probabilistic analysis, things that would take exponentially more resources to compute when it comes to a binary system, qubits actually have its very superior, like it has its superiority when it comes to this field. And I think it's where like it comes into play. Like in probabilistic analysis, it's very important for military to do computerized simulations for predictive like trajectories, and of course maybe also for scientists for geology or things like that, for prediction of earthquakes or all these things. A quantum computer can actually be naturally more useful in these cases. So I'm actually optimistic about the way that I think we find a way to solve this pre-existing problem, especially like when it comes to below zero. People are already trying to overclock CPUs to like 6, 7, 8 gigahertz with like binary system by using liquid nitrogen. So like I don't think these things are not like these are already attempted when it comes to traditional computing. So I don't think it's a problem to maintain a low temperature environment for quantum computers, and they should be actually stored in labs or places where this can be achieved, not in the field, let's say.
Let me disagree somehow on what did you say, that, the coherence issues. I mean, depends on how are you going to use this problem as a linear problem or a non-linear problem. If you're going to use it in linear problem, you have the factors of different, elements that will affect the coherence. But the main issue about the coherence of the quantum states is the temperature and also the vibration. But, I will say, following your presentation, that probably it's going to be an ideal case, let's say, back to the headquarters, to the military headquarters, that they can control bigger computers, smaller units in order to make the prediction. My second question comes to what did you say, if I got it well, about the energy demands. We know that with the introduction of AI, the consumption of energy is like 30, 40% more than the conventional one. So if you combine now the quantum computers, even if you are going to use hydrogen, and if we are going to use the AI elements, the energy consumption will be amazing. And this is something that concerns a lot the community. So what is your idea about the energy consumption? Because this complicates the things.
I actually, this is a very good question, and honestly, I don't really have a very professional answer for this, because I know that like in the industry of AI, this is a very like emerging problem that people are saying that actually AI is very energy consuming, and now like according to predictions, like in a few decades, like the power consumption just for the use of AI and large language models is especially like for processing and maintaining these things, the computing power is actually going to dominate the electricity use in the future. But I think like the main reason for that is that we're using AI that actually concerns every single thing possible with our lives. And I think for military, especially like for operational uses, I think people should actually design a more specific language model that actually fits only the situations that are needed for a specific operation. And I think this is a way that we can actually save the battery, like save the power consumption. So we have a smaller language models, and which means like we can run these with lower memory bandwidth and lower capacity of memory. So like there's going to be less power required for the CPU or like for the processing units or something to like process. But actually in terms of energy, and I think we can also address the fact that we need a very ideal situation for quantum computers to work on. And like in terms of the computing like energy, we need to actually invest more energy when it comes to like just maintain a quantum computer. I think that's also a part of problem. So like what I can say like regarding this issue is that first, we can create a more specific language model to work for a specific operation. So we're not going to use a very universal language model that will like consume a lot of redundant power. Just like what people say that it costs $1 million of power just to say thank you to ChatGPT. So of course, we should not let that happen when it comes to military use. That's the first. And another thing is that we should find some more efficient way to produce energy with less loss in the process, with a more greener and more efficient like energy production that can actually meet our need for electricity in the future. Because I know that like according to the current trend, it's very hard to like maintain the need. So we need to find some better ways. There are a lot actually yet to be implemented, like hydrogen power, or I don't know, like maybe third geothermal power, or even like nuclear power. Like I mean, like they can actually be very cooling when maintained properly. So like we should actually also try to produce more power if we need them, while trying our best to like consume as little as possible, basically.
Thank you very much. I totally agree with you that we need to use more efficient energy sources than the ones that we are using. Thank you, Jonathan.
Welcome.
Yeah, Bogdan?
If I may, yes, I have a question that sorry. In your presentation, you mentioned that the combination of quantum computers and AI can help us with calculating trajectories of ballistic missiles, as you said. But as we see on the modern battlefields, such things as long-range ballistic weaponry is is going a bit obsolete, turning more into like more smart weapons. How can the quantum computers with combination of AI respond to this shift towards the more precise and smart weaponry that can't be predicted so easily?
Okay, I think it actually, yeah, I think you're right. And what I think that they can do is kind of a problem that is like related to the advantage of quantum computing, which is to calculate what's going to happen next. So I think maybe you should elaborate on, like you said, that trajectory, like prediction is going to be obsolete. Like, I'm sorry, I didn't really understand it fully.
Well, I'm myself from Ukraine, as you probably understood,
Yeah,
and
and I'm from Israel.
yeah, statistics says on the Ukrainian front lines that the 80% of all target destruct neutralizations of they are like made by drones, made by something that is ratherly not really can be predicted because it's moving directly controlled by pilot. As we see with more smartification of weaponry, laser targeting, it's really well. I forgot what I was.
Okay, I think I understand what you're talking about. So basically, I was not talking about these like human-controlled drone devices. I think it was more related to traditional missiles or something. Like that was actually an additional point, and that's why I said last but not least or something. Like that's more additional point of my presentation. And actually, a person in my group, like in my project, actually elaborated on. I think that's called LAWS or something. Like it's related to drones, and I think he knows this a little more than I do. What like the main focus of my project is about like to dig the potential of quantum computing. So like I'm really sorry, but I don't really know like if quantum computing can actually help it, specifically in this case. What I can say is that, like as I said, it's very good in probabilistic analysis. So maybe there's a way that we can predict, even if it's controlled by someone else intentionally, we can still find a way to do it like in an infinitesimally tiny time to like learn the behavior of it, and maybe it can still create a very like small range of possible direction of movement in a split second. And maybe that's something that can help us. Or maybe on the other hand, we can also use something that can be humanly controlled to counter-strike these things. That's what I can think of. So yeah, I hope I answered your question.
Yes, completely. Thank you.
Okay, can I ask a question or
Yeah.
and give a comment, or like I want to actually address kind of an elephant in the room. I'm not a technical person. Like I'm a linguist. I come from humanitarian background, and I studied artificial intelligence in my master's degree in 2005, 20 years ago. And of course, I'm very much involved in testing different AI tools and everything. I've heard about quantum computers. I read about them. I studied them with my Technion students. And I always knew that once those machines become mainstream, like the quantum computing becomes a reality, it's going to be a huge change in the world. Like everything will change. It seems like a similar revolution. So AI is changing everything, whether we understand and realize it or not. And quantum computing will have a similar or bigger or a much, much bigger effect, something like that. Now, the topic of your presentation is military application of these super powerful technologies. And looking at our reality, I feel like I'm always optimistic and excited about innovation and everything, but now I feel like I'm a little bit worried, and I wish we would go back in time to like, can we go back to like Stone Age when there was no computing, no AI? Because we're talking about these very, very sophisticated military advancements that are not going to be ending anytime soon, and they're just developing, and lots of countries now investing billions and billions of dollars and euros and whatever in that development, in that direction. I feel a little bit apocalyptic. I don't know if that's the right word. And I don't know if it's a question, and of course it's not to Jonathan, it's to all of the students who presented with you. And maybe anyone else who want to say something about it. Do you feel like maybe there is another way, another path for humanity to develop and to implement this technology into kind of making us alive rather than, killing each other? Yes. Thank you. Sorry if I just had to express that. Bogdan,
If I may, yeah. This whole story with like quantum computers that's combined with AI reminds me of one short story. It's not really short, but is a way of I have no mouth, but I must scream. Scream. If you read this, I don't remember the author, but the whole story is about is around a supercomputer, military supercomputer that destroyed the world, and just to its like hatred towards humanity and its touch, or the story touches all of these possibilities of what will be if we'll give a gun to a robot. Will it turn to us, and how? What if? What will it feel when it will turn this gun to us? Really interesting story, and all this quantum computing with AI gives me those dread apocalyptic vibes. I don't know.
So I'm not alone feeling that, right? Bogdan?
Yes.
Kostas, what do you say? What do you want to add?
I would like to see more positive the things. I think that, this kind of system also protect lives. I mean, if you have this kind of system, you can protect your life and you can experience this very well. At the same time, they are even when they are going to be used for defense reasons, I mean, they are more selective. I mean, you identify what you would like to, let's say, neutralize. This is my point of view. So they can protect life because they can deteriorate or can defend people from attacks, but also they can identify, more precisely than you send a napalm. So in Vietnam, they said napalm and they burned everything. Now they can select. I mean, if you can have a positive view on this thing. On the other hand, there are two industries that we test any technology. This is with F1 Formula One, whenever you are doing anything around systems, either is for aircrafts or either for cars, any system is testing in F1. And the other test field is the military because of the harsh conditions and the things they should operate 100%. So, I mean, these are, the realities right now. So this is my point of view. I'm not going to bring the catastrophe because in this case, computers, they bring the catastrophe. I mean, I think that everything happens for good and everything happens towards the progress of the civilization and the human beings and the well-being.
I like your approach, Chris. That's why it's good to have you among my friends. One last question to everyone who understands the field. Quantum computing, is it like you were talking about it as in theory? Is it real? Is there any progress in this field? Are we almost there? Is there a prototype? Like what's going on in terms of quantum computing? Is it just a theoretical concept that is...
It's not a theoretical concept. I think that Jonathan, has mentioned this. I mean, it's something that is moving with a great speed during the development. I mean, if you follow the, oh man, I'm tired now, the superconductivity, I mean, you can see that, how semiconductors, they can operate closer and closer to the room temperature. We have examples of this technology regarding semiconductors from the electronics point of view. The trains in Japan, how fast do they move, exploiting superconductivity. Regarding computers, it's a matter of time. I mean, these systems to operate very close to room temperature in order to reduce the energy load that they need. So it's almost a reality. And now Jonathan complicated the things, but this is how technology is moving, like to combine with AI and provide and analyze all this data, that all these combinations they can follow. I mean, for the people that they are not from the physics or from the engineering, fundamentally, I mean, you have the orientation of the spin of the electrons, in any kind of directions, and this provides, the encoding of the information, not just zero and ones, but directions of the spin of the electron, around its axis. This is, so it's not a theoretical part, it's a very applicable technology.
Thank you very much. This is fascinating, and I really enjoy our discussion. So let's move on. We have two more presentations. We have, hold on, Pablo and also Mario joined us. So, Omri, will you take the floor and introduce the next speaker?
Of course. So the next speakers are cybersecurity and AI, challenges and opportunities.
I don't think we have, I think it's Nikita's part, and I don't see Nikita here. It's a student from Ukraine with another colleague. Are you guys here? Are you there? Maybe let's skip this one and go to the next.
Okay, so this is the last one. Visualizing the invisible, AI's radar lens on particle collisions.
Excellent. And this is Pablo's,
Oh,
right?
this is not the last one, there's one more.
Yeah, we have
after.
one more by Mario. Yeah.
Okay, hello guys.
Hello.
You can see my screen, right?
Yes.
All right, so I'll try to be really fast with everything, so no, I won't bore you to death. Okay, so I want to talk about research that we have done. When I mean we, it's me and my research team. We are particle physicists, and what you're seeing in the right part of the screen is a transversal cut of the LHC. The LHC is a Large Hadron Collider that's located in CERN. I don't know if you heard about it, but we'll discuss more about it right now. So first, I wanted to describe who are we. As I said, we are a group of particle physicists that are really interested in getting to know the fundamentals of the universe. And how are we going to do that? Well, basically, in really simple terms, just smashing particles into each other. That's the way that we are trying to discover the fundamentals of the universe. We are a research team that works together with CERN, especially one experiment at CERN that's called the CMS. And we have access to their data sets of the previous rounds of the LHC that were done some years ago. Okay, so let's first understand the problem, right? How do we do this this is smashing particles into each other. So it's really simple. If we want to try to understand it, basically what we do is we take an electron, a proton. We take another proton. We try to smash them into each other at really high velocities that are near the velocity of light. So what happens when every particle gets when we get a collision, we produce a lot of energy and a lot of particles. We have heard something about Einstein equation. We know that matter is basically energy. So we have a lot of information in every run, in every collision. So basically, we have a really big challenge of big data here in physics, especially in high energy physics. And the first one is the massive data volume, because the CMS experiment at CERN generates petabytes of complex data with approximately like 40 million proton collisions occurring each second. That's a lot. That's a lot. If we would let the CMS run for a long time, let's say a day, we could actually get enough data to cover all the CPUs existent in Earth right now. So there's a lot of data we have to process. And as we have a lot of data, we have the other problem that's really time consuming. The analysis of each collision is really time consuming, because the traditional analysis that we do, we use techniques that can be extremely time consuming when dealing with such vast amount of high dimensional data. And finally, these collisions are not easy to analyze. They have a lot of complex patterns, because we do have to identify rare events and subtle patterns among billions of collisions, and that requires sophisticated analytical approaches beyond conventional methods. That's what we're proposing right now. But what actually happens inside the LHC? Well, this is a simulation of what happens. As I showed you before, this was the transversal cut, and what happens is that in the middle here, the two protons are colliding, right? This releases a lot of energy and a lot of particles in all directions. These particles, each particle that is produced has its own velocity, its own momentum, it's the same thing, and its own energy. And obviously, it gets detected by the colorimeters that are the sensors that are detecting each particle that goes through it. And as you see, each point of this, it's like one set of data, and one set of data has a lot of rows in it. It's a lot of information that we have to produce, that we have to analyze in order to understand what kind of particle was produced in every collision. So this is a problem, right? Because we have a lot of information, and we just have simple techniques of analysis. Now we are introducing an innovative approach, and it's really simple. I'm going to try to explain it in really easy words. So first, it's a novel approach that converts high energy physics collisions information into visual images, okay? And this transformation allows us to leverage the power of convolutional neural networks. So as I explained before, what we are doing is we are taking each particle that is produced in each collision, and at that particle, we're assigning them a circle. Literally just a circle that we can represent in this diagram here. This diagram we have in the x-axis, the eta. Eta represents the velocity of the particle. We're going to represent phi in the y-axis as the position of the particle, in what direction is the particle approaching the detectors. So for every particle, we're going to create a different circle. For example, if we have muons that are cousins of the electrons, just if you haven't heard about them, we're going to create this type of circle that has some red in it, but it's not so red, and also has a different radius, as you can see at these different circles. So how we decide on the radii and the color and that? Well, basically, what we are doing right now is using a circular representation that is really easier for a machine to understand. So we are mapping the position, and so each particle position in the detector is mapped to coordinates in the image. That's a way to preserve spatial relation, because that's something really important we have to take in mind when we are doing the analysis. After that, we make a momentum, encoding of the momentum. We encode the momentum in the radius. So basically the radius of each particle, each circle in this case, is proportional to the particles from its first moment. That provides a really important key in energy information because, well, if we follow the energy momentum equation of Einstein, we can understand everything with the momentum, just the momentum. And also we color code it. So different particles type are represented by different colors: red for muons, blue for jets, and black for missing energy. And missing energy are those particles that we don't quite know, or we are not quite sure what are they. But we have to always conserve energy, so we have to put them in there just to not break physics, basically. And what this produces is a visual pattern recognition and this representation creates distinctive visual patterns that neural networks can learn to associate with specific physics processes. So what we are doing, basically, with the neural network classification is this. First, we create an image, right? Every collision data is transformed into a pixel image with the particles being represented as circles, as colored circles. After that, we do a feature extraction. What that means is basically we use the computational neural network, let it extract the key features for these images through multiple layers of processing. After that, we create a pattern recognition. So the neural network learn to recognize patterns associated with different particle processes and resonances for every collision, obviously. And finally, what we do is do a classification. So the system classifies each collision event into categories like a Drellian process, a Higgs process, or any other process that could that the neural network could learn. That's what we are doing, and we were really interested in how or in what architectures of these CNN models we could be using. So we practiced with some of them, and we came up to the conclusion that always ResNet is going to be one of the best ones that produces almost the 84% of accuracy. And I think Bogdan has something to say right now in this part related to how this architecture works.
Yeah, sorry. It's my turn to say. I have a bit of information about like how this works, how the AI machinery itself works, because I have had a bit of experience with this, with machine learning. Well, if you may return, please, to the previous slide. Yes, about pattern recognition. How does this work? As Pablo said, it's using the image and by how do you say that in English? 1 second, I'm forgetting the words. And by saying to the AI, these colors means this, we are making it learn, because AI itself is rather really intelligent, but in the meantime rather stupid. It will say whatever we'll tell them to say. If we say the color yellow means that then AI will repeat after us that this color will mean yellow, even if it's mean green. It's, what is it, Pablo? Am I saying something wrong?
Sorry, what I didn't hear you. I'm really sorry.
Please repeat.
What did you say? Sorry.
Am I saying something wrong, please?
No. Everything's fine.
Yeah, sorry. Just don't mention it. I'm a bit anxious, nervous. Either way. And if we'll feed it with the wrong information, then the AI will answer us with the wrong information. That's simple. It all comes back to the human factor, to the humans, to us, to people that will teach the AI how to work properly. Yes, it will learn much faster than human being and can like absorb the information that takes years for a human in like days, but it still can make mistakes if we'll feed them this information. That's why most of the time for the AI to learn, behind all of this process stands a rather large amount of underpaid students that are asked to like tell the AI over and over and over and over again that yellow means yellow, green means green, and the same process. Most of the time, it's actually, well, I can share you how we in Ukraine teach AI on governmental level, because it's easy way. So in the government projects, the Ministry for Economics, for example, it sponsors the hackathons that gather all the teams that will teach the AI in this basic labor style, like bunch of students, bunch of laptops, and they all making squares. They all saying that yellow means yellow. It's a rather long process, yes, but it actually have some rather good results, because after AI learned that yellow means yellow and greens means greens, if it add yellow to green, it will have it can like understand it by itself what color will came out eventually, something like that. I stole a lot of time of yours already. I will end on this one.
Thank you very much, Bogdan. Well, yes, it's really important to understand a part of it. Yeah, definitely we do, relating to what it said, we do have a lot of improvements that we have to make. Even as we can see here, we just have the 84% of the accuracy, even though we didn't train the model a lot of times. So that's important. Well, I wanted to finish talking about something important. It's about how one of the motivations that we actually did this research. And well, let's talk about something about the future of AI in particle physics. We didn't even actually thought about it before, but as we came into this really big, interesting, and important problem of complex and time-consuming analysis, we discovered this. And well, we can pick three really important things, and these are this. So enhance discovery potential, right? Because AI techniques can help identify rare events and subtle patterns that might be missed by traditional analysis methods, potentially leading to new discoveries in fundamental physics. That's the main point, right? We're going to have really accelerated analysis. That means that machine learning algorithms can process and classify vast amounts of collision data much faster than conventional approaches, speeding up the research process, which obviously is going to be really useful. And we cannot stop there. We could have border applications. The image-based approach demonstrated in this research that it could be extended to other physics processes and experiments, not only those that I work here. So we are trying to create a versatile toolkit for high energy physics analysis that's going to be really useful for us, right? For us and researchers later. And well, I just wanted to say that. And regarding the AI used for this presentation, well, Gamma was the tool used for creating the visual slides. That contents are for the research made by us. And well, if you want to read more about it, we have the references and the link to the Open Data's portal. That's always fun to read. And thank you very much. That was it.
Thank you.
Thank you, guys.
Thank you so much to Bogdan and Pablo. Our next presentation is man versus machine, the emulation logic.
Do we have time for questions for Pablo and Bogdan? Maybe if anyone has any questions, maybe we can also address them all at the end after the final presentation. Okay. Mari, you can share your screen now.
Yeah.
So today we had a presentation from Israeli, a team of students, and Italy, Ukraine.
Do you see my screen?
Yes.
All right. I was waiting this moment from last week. So we'll start. The title of my topic is demolition logic. That is the answer for a one simple question, that is, how can we apply what we study in order to find real solutions in the work world? So we'll go to analyze the meaning of demolition logic, how demolition logic is able to reason, and how demolition logic is able to produce a determined output. We'll start from the meaning. Demolition logic is a model developed with AI capable of analyzing the strategies of a given player in order to predict the goal that he aims to achieve. Note that we are analyzing demolition logic in the business world, so the player is equal to a company, for example. Now, first that we analyze the reasoning of demolition logic, we have to introduce two theoretical foundations. The first is the operations research, also defined as the management science, that with the help of algorithms and mathematical models studies real problems in order to find real solutions. The second is the dimension theory, that is a direct consequence of the rank theorem. The statement is let x vectors. For those people who don't know what is a vector is an element made up of n components. So if we take x vectors and we have a number of components, we will have at most n linearly independent vectors. But what means linearly independent? We'll explain the meaning of linearly independent with an example. If we take three vectors, each one is made up of two components, and for example, the first vector has component 0, 1, the second vector has component 1, 0, and the third vector has component 1, 1. We can simply see that the third vector is the result of the algebraic sum of the components of the first two vectors. So this is very important for the rest of the presentation and for the reasoning of demolition logic. So in this slide, we'll see a neural network that is the main structure of every AI model. Meanwhile, in the second image, we'll see the digraph that is one of the main tools used in the operations research. A digraph is a dynamic structure made up of nodes and arcs. Arcs are the links between those nodes and allow us to understand how to reach a determined node starting from one. Two things: note that arcs are oriented, and the second thing is that every arc has a cost associated that in the operations research is named weight of the arc. Now we're facing the first crucial point of this presentation, that is how the database records information. Now I ask you to remember for a moment the definition of a vector, because in this model the database stores its information like a vector made up of two components. The first component is the action, and the second component is the cost associated to that action. Note that we're providing a qualitative model of demolition logic, but we can consider many and many other variables, like, for example, time. In that case, the database will store vectors at three components: action, cost, and time. Now, this is the main action that demolition logic does in its reasoning, because how demolition logic is able to classify his inputs. You're seeing independent and dependent action. That are two words that we already seen in the dimension theory. Because the independent actions start a walk in the digraph, meanwhile the dependent actions are in the middle or they end a walk in the digraph. First of all, what is a walk in demolition logic and what is a walk in the operations research? A walk is a sequence of arcs that explain how to reach a determined node starting from one node that is called the origin of the walk. So, in demolition logic, the origin node is simply an independent action that is not linked with other actions that are stored in the database and is starting the walk, so is starting the strategy. Meanwhile, dependent actions are in the middle because are directly linked because they are consequence of the first action that is starting a determined strategy. And there is obviously a dependent action that is the end of the strategy. So we have mentioned also in the slide only two analyses, because there are many other analyses that are possible to do on a digraph in the operations research. The first is the research of the minimum and the maximum path. Because if we have multiple walks that start from the same node and ends in the same node, means that the same strategy could be reached with at least two set of moves. Now we have seen that every arc has a cost associated. So if there are two walks in the same strategy, we can do the algebraic sum of the two different work. So doing the algebraic sum of the cost associated with every arc that is in the walk. And in this way, we can obtain the maximum. So the path that has the higher cost and the minimum path that is the walk that has the lowest cost. The second analysis is the research of bridge nodes, because we can have in demolition logic a single action that is linked directly with two walks. This is very important because in this way we can understand if there is one single action that is valid to be included in at least two or more strategies. So we have arrived to the essence of demolition logic. You can see the man that is in panic because he understood that, that the machine is emulating him. We have seen the reasoning, and the last thing is the output, how demolition logic is able to produce a determined output. This is the crucial point of this presentation, because the user needs to communicate to the program when it's the moment to enter in the predicting, or better, in the demolition phase. In that moment, demolition logic stops to store informations in its database, takes the strategy that doesn't have an end, and at that moment, he is able to compare all the walks that are stored in the database. And in this way, demolition logic is able to anticipate that player and predicting the goal that he aims to achieve. Now, I want to thank all the people that paid attention to my presentation. This was a slide that was made for the AI icon the last Wednesday.
You're still in the conference. Thank you, Mario.
So
very much.
I leave here my contact because I think that, and I want to underline that this topic is only a qualitative model on demolition logic. I know that in this call there are people that are knowledge about these informations, and I think that it's possible. I think that absolutely I have to do a quantitative model of demolition logic. And second thing, I wanted to underline the commitment of Helena and Konstantinos to carrying up this course. And I wanted also to thank the impact staff, the whole impact staff, because in this way we can discussed, there are students from all over the world that are discussing on what they are studying. And this is fundamental. Thank you.
Thank you very much. Wow, this is really impactful and it makes us proud, doesn't it, Costas? Thank you so much. Very, very interesting. It was like looking into the black box, right? They discuss how does AI work and think and why is it creative, and like you gave us some real foundational explanation with this theory of the emulation logic. So thank you very, very much. Please let's maybe have some questions discussed. Does anyone have any questions? Yes, Costas.
Yeah, I have a question regarding the, first of all, thank you very much, all of you, Mario and all the students for the participation, because without you, nothing can happen. I mean, we need the engagement of the students, and everything happens for students, by the students, for the students, and we are learning. We are students as well. So we have learned, I learned a lot of things from your side. I would like to ask a question regarding the neural networks and how much the neural networks are related with the quantum computers that we have discussed before. I would like your opinion. I think that this is a question to the guy from the particle physics. So how much he relates the training of the neural networks, or the relation of the neural networks with quantum computers, or what would be the impact of quantum computers to the neural network? What is your feeling, Pablo?
That's a really interesting connection that you're made in here, but because obviously having a quantum computer as tool for training any neural networks would be really, really important. I mean, the time consuming analysis that has to be done to actually train the neural networks would be done in so few time. But now the problem is that, as we discussed before, if we were able to do so, maybe those really big institutions, like maybe CERN has, like I have this example in mind, maybe CERN has the ability to actually get their hands into something like this, but I don't think it is like really nearby. I mean, we've been hearing about neural quantum computer for a long time ago, but I don't think it's going to come anytime soon, and it's really, really sad because it could really helps us, also researchers. I mean, but yeah, I mean, it would be really, really useful. Yeah, definitely.
So, Pablo, without be within this field, I will say that quantum computers will increase, the legs of the neural networks will increase. The combination of the pathways that we can reach a conclusion faster.
Yes, sure.
Okay, thank you, Pablo.
Thank you very much. Any other questions or maybe comments? We will conclude the event, the AI icon, in just a few seconds, I believe, and we will thank our guests. We have some people who are not part of the course and they joined to follow this very interesting discussion and your fascinating presentations today. So thank you to our guests, and we will soon move on to our second part of the meeting today, but let's see if anyone else wants to add anything. You can also send reactions on Zoom since we are in a virtual environment. You could go to reactions and just congratulate each other on the successful completion of this conference. Bogdan, yes, please.
Yes, I have something to say about all this course. It was really actually cool and like really awesome trip. I don't know, like journey and all. It was like really funny, really interesting, funny too actually. To make our presentation, our project as it is completely by ourselves. It's something that is well rarely to be participated in. actually. It's a rare opportunity, and not with some like generic topics. AI, the topic that is like the most like popular topic right now is definitely AI, and we are talking about AI, about one of the like most advancing and popular things in our times that changed our world perspective, not in decades but in years, if only if even months, I can say. So I'm really grateful I was a part of this course. I'm really enjoying all of that. Thank you, Elena. Thank you, AI Impact. Thank you all for having me. I don't know. It was awesome.
Thank you so much. Congratulations. Congratulations, everyone. You've done an amazing job. It was supposed to be really student-centered, and you did an amazing job working on your presentations, working on your projects, organizing this event from scratch, from A to Z, completely using your creativity, using lots and lots of AI tools. I think our guests would be also curious to find out what exactly tools we used, and we will share that information on our website. In the coming session, we have, as I announced earlier, we have 2 additional guest lecturers joining us next Wednesday and in 2 weeks. So something to look forward to. But I'm again very, very grateful and thankful, and I think you've done an amazing job. Congratulations to everyone. And let's proceed to any other comment or final concluding remark. And if not, then this is recorded. The guests and whoever is interested to follow the recording will receive the link to our YouTube channel, and you can subscribe and follow. Any other questions or comments? Final reactions? If not, then we are moving on to the final session. Mihailo, do you want to say something? Yes, go ahead.
I just wanted to give a quick comment. Wanted to thank everyone who did an amazing job on organizing all this event. Everyone did fantastically. So yeah, everyone who worked with me and everyone who worked without me, thank you all, guys. You did an amazing job.
Wonderful. Thank you very much. Thank you. I appreciate your contribution, Mihailo, as well. You are one of the leading leaders. So well done to all of you guys. All right, Kostas, now the floor is yours. You have about 15 minutes.
I mean, now,
want.
what can I do now? I mean, it's like to try to think after Frank Sinatra. It's very hard for me to do this. You know, the students, they did an excellent job. Not students, the colleagues. You know, all of them, you know, all of us, we are colleagues. And you need to, I mean, I feel proud of you. Without being with you, I feel very proud and, you know, following you also in Hanya and in these online sessions under the supervision of Elena. I mean, and also Rafael, because there are a lot of teachers behind, you know, Impact.